Today I'll introduce a new geometry-accurate dynamic avatar reconstruction framework TGA, True to Geometry Avatar Dynamic Reconstruction. At the bottom of the slide, you can see several visual examples, reconstructed mesh and the textured avatars performing dynamic facial motions. In many recent 3D Gaussian-based methods, such as Gaussian avatars or Gaussian head avatar, the focus is mainly on photorealistic rendering, capturing how the face looks rather than how it is shaped. These methods can produce visually appealing results, but their underlying geometry is often inaccurate or unstable. As a result, the reconstructed surface may drift or collapse in certain regions, for example, around the mouth or eyes, which makes it difficult to extract reliable meshes or maintain consistent facial motion over time. So while they look realistic, they don't preserve the true geometry of the face, and that's exactly the gap we aim to fill with TGA. Now that we've seen why geometry accuracy matters, let's look at the key ideas behind TGA. Our goal is to reconstruct dynamic head avatars with geometry-accurate surfaces and efficient mesh extraction, even under motion and complex expressions. To achieve this, we first introduce a perspective-aware Gaussian transformation. It integrates Jacobian-guided deformation and homogeneous projection, allowing each Gaussian to correctly respond to perspective and motion. This is the foundation for our true-to-geometry modeling. Second, we build a dynamic BVH tree that updates frame by frame using branch rotations and pivoting. This structure dynamically filters hopping points, which represent fast-changing or deforming regions. Finally, these hopping points are incrementally triangulated using marching tetrahedra, which enables both fast mesh reconstruction and temporal consistency across frames. In short, TGA combines accurate geometric modeling and efficient dynamic updating, forming a unified framework for high-fidelity 4D avatars. Next, I'll show how these components work together in our framework. Given multi-view RGB sequences, we first track facial dynamics with flame. During the perspective-aware transformation, we applied Jacobian-guided deformation and homogeneous projection for accurate geometric modeling. Then we optimize the Gaussians with a combination of photometric and geometric losses. After optimization, we build and dynamically update a Gaussian BVH, where BVH pivoting adaptively filters hopping points, enabling geo-accurate surface extraction via marching tetrahedra. We illustrate this topological simulation of fast avatar reconstruction in the BVH structure. Here yellow A, red B, blue C, and green D bounding boxes correspond to facial features, alongside its tree representation of the avatar. As facial expressions occur, these bounding volumes are locally refitted according to the movement of enclosed Gaussians. As the extent of box D significantly expands to tightly enclose both A and B, the BVH tree achieves branch rotation, swapping between B and C, to reorganize the hierarchy and do topological simulation. Now I'll show some geometry reconstruction results to show how TGA actually performs. Compared to baselines like HRN, NHA, Topo 4D, and SurF head, TGA produces cleaner and more accurate meshes, especially around high-frequency regions such as lips and eyelids. Here we show the mesh rendering results of our reconstructed avatars using flat shading. Even without complex shading models, the results appear realistic and temporally stable across frames. Here we show the novel view synthesis results of 3DGS rendering. As you can see, TGA maintains stable results across frames and subjects. More detailed and dynamic results can be found in our paper and the project website. Thank you for watching.